Hi, everybody. I'm really happy to be here. This is my talk on information theoretic representations of agent dynamics as set intersections. It's kind of a long title, but I will be very concise in my definitions. I'm based out of Boston University, and we have funding from NSF grant and that number. So the take-home message I want everybody to know is that this is a new model for agent environment dynamics. And by new model, I mean pretty much a new proof system. This is in algorithmic information theory, and I guess the central theorem that we proved was that agent complexities has an exponential distribution. And I'm happy to say that this resulted in a AIT paper with Leonid Levin, who did Levin search and a lot of the complexity variance that we talk about, and that was released at early August, so if everybody could look at that. And so it's very exciting to have an AGI paper that kind of gets exported and helps out this other field, which is AIT. So I think that's a really exciting thing, is that there's a lot of theorems out here and a lot of stuff people are doing, and I feel like it's very mineable and can be exported into other areas. So now I'm going to talk a little bit about agent environment interactions and Hooter's model, and then how that can be changed around into a different structure to create different types of proofs. So this is an agent environment interaction. There's a knight and there's a dragon, and then this is Hooter's universal artificial intelligence model. So on one hand you have the agent, who's the knight, and the other hand you have this environment, which is the dragon, and you have this interaction going between them. And one of the interactions is the perceptions, which is a reward and an observation, and then the other is an action, which the agent does. And Hooter's brilliant innovation was that the agent and the environment can be represented as Turing machines. And then so here are the rewards and observations, here are the actions. So, and then he used Solomonov's universal prior, or the Solomonoff-Levin universal prior, and he was able to create the singular formula. And this is probably the most exciting thing I have read as my PhD career, because I feel it incorporates all of the theory that's interesting in artificial general intelligence. And it's a simple formula, but the complexities of it are very fascinating. And again, it resulted in a paper in traditional AIT theory. So what is this saying? Well, each environment is going to be weighted by its Kolmogorov complexity, and that's Leonid's variant, which is the prefix-free version of that. So if you just sort of do kind of a Bayesian summation over all of the environments, you get this universal environment psi. And that universal environment, if you have an agent that's optimal to that, then you get all sorts of interesting possibilities. So K, I mentioned before, this is the size of the description of X. I use capital K because it's Leonid's variant, which is prefix-free, so it can converge. But that's about as much as the math that I want to talk about. And now let me talk about a general conjecture I have, sort of about where I think things will be going. So we have these two measures. People have been using them in really exciting and creative ways throughout the conference. And one is a discrete measure, which is Kolmogorov complexity, and that just maps to a code, and that's an integer value. And the other one is the universal prior, which is Solomonov's measure, and that's sort of a combined. That's sort of a combination of the two, and then with the coding theorem, they're actually equivalent, and they're the same thing really. You can in many papers you actually define k of x in terms of log of x, so they're basically the same thing, and there are two different types of information measures. Now we have interaction, and I don't want to encapsulate Hooter's model, but I have to make some sort of generalization. So this is universal artificial intelligence. Hooter's model uses a lot of the proof techniques derived through Solomonoff and universal induction. So the question is there a discrete version of interaction where you can develop a whole new field and leverage all of the interesting combinatorial and algorithmic proofs of K of x and apply them to interaction? So I actually believe that there's actually a symmetry that is related to universal artificial intelligence, and that is non-cooperative games and Nash equilibriums. And I was able to take the universal artificial intelligence model and put it into this discrete structure, and I can prove some very simple theorems about it. So I feel like it's been a very successful endeavor. So what am I talking about? So let's translate these agent environments, which have probabilities, and that's fractions, and fractions are sort of hard to use. So let's just put them into a non-cooperative game. Let's squash time into a simple strategy space, and all the interactions are now pure Nash equilibriums. So let me give you an example of an interaction between two players. So now we have two players, and you have player A and player B. And player A plays rock, and player B plays paper, and then he copies A's move. So what you do is that you encode this into a Nash equilibrium game. So you list all of A's possible games, and you list all of B's possible games. So these are all the games that A can play, and these are all the games that B can play. And you look for the intersection of these two lists. And the intersection of these two lists is the set of pure Nash equilibriums. That's basically the only game that A and B can play. If there's uncertainty, then they can play different types of games, but in this case, it's only a single intersection. So another way to look at it is through a Venn diagram. You have A and B. That's the list of their possible moves. That's B's list of possible moves, and the intersection is the intersection is the set of games that they play. So these values represent text and strings, so the natural thing is that you can apply complexity theory to it, in the sense that now you can derive interesting properties of it based on the fact that you have this encoding. So basically what I'm doing is I'm taking all interactions, and I have two sets of strings. The intersection of the two sets of strings are the interactions, and you develop a lot of interesting properties of it. So A and B are Turing machines, and they have an interaction X, and the information revelation between them will be less than the Kolmogorov complexity. And this is Kolmogorov's variant, not Leonard's. So how does the paper work out? Well, basically you encode all this complicated dynamics into two sets of strings, A and B. Then I basically develop a series of definitions in terms of the learning capacity of a player, and then you talk about conditional complexities, and then you import something called the randomness deficiency. So basically I'm building up definitions, and then I'm importing combinatorial proof techniques from very recent literature in algorithmic information theory by Vitani and Vereshchagin, and from these proof techniques you can derive some very simple theorems. So I'm going to go through a couple of the theorems. This one's sort of boring. Theorem 2 is superfluous information. If you have A and B, they have some sort of interaction, then there exists a B prime that can interact with A, and whose complexity is less than the mutual information of A and B. So it's very simple. It's just saying that if I interact with somebody, I can develop an approximation of that person and still have the same interaction, and all of their information is contained within me. So this one has a little bit better interpretation, and that is that you have multiple agents, and this is probably the easiest one to understand, is that if you have 2 to the k agents who can interact in some sort of way with B, or have 2 to the k Nash equilibriums with B, then there exists and they all have a certain complexity, then there exists an A prime that can interact with B that has Kolmogorov complexity less than or equal to R minus K. So basically, when we're thinking about all these agents in environments, we now know that they basically have an exponential distribution in terms of the complexity. There does exist environments where this doesn't occur, and Lenin and I proved that if this doesn't happen, then B has a lot of information with a halting sequence, and in this case, it's a very unnatural thing, and there's no halting sequence string that's been produced in the history of the universe. So that's it in a nutshell. Thank you very much. Don't mean to be quick, but I guess that's my nature. So that's it.
So you're leaving you have to go really quick?
Yeah, to San Francisco.
So we'll have the questions for him right now. So go ahead. You have a few minutes to ask questions.
Any questions? No? Okay. Thank you very much.
Thank you very much. Let me tell you first about my work of several years. I was initially motivated by refactoring of software. But then refactoring happens to be universal because what we refactor actually is our thoughts. So that just increased my interest. My approach is computational experiments. And in the course of that kind of research about refactoring, I found a number of things. For example, I noticed that partially ordered sets are a very good knowledge base. Most of all because any system can be converted to knowledge, to partially ordered sets representation. Quite easy, I would say. I also found a new type of inference that I named emergent inference, which in fact had been predicted by Helmholtz in 1850, experimentally by studies of vision, and he said it would happen in the brain. And now I have found the mathematics of it, and I named it emergent inference. And I proposed that as an explanation for emergence and self-organization in complex and dynamical systems, and also for intelligence and emotions in the brain. Here's one of my computational experiments. I call them brain experiments, also the brain is not involved. I start on the left with some body of knowledge. For example, it could be a problem statement for an object-oriented project. And I give it to an analyst on the upper row, which is the brain, and the analyst creates for me some structures that I call the natural structures. Natural because they have been created by the brain, which in this case would be the object-oriented design. Of course, it does not have to be that, but there are many possibilities, but that's an example. And then separately from that, I convert the body to a partially ordered set representation, apply the emergent inference to it, and I get some structures that I call predicted structures because they are mathematically predicted by the procedure. I compare the two, and I did a number of experiments, and the two compare pretty well. I was surprised myself how well they compare. So apparently I can reproduce the work of the human analyst by using emergent inference. Here's my first experiment. That's where I discovered how the inference itself. On the left is a very simple program which I scrambled in a bad way so it doesn't have any organization or any visible structure. All the X's are input data that are given. On the left, we have variables that have to be initialized by the program. That's all there is. On the right-hand side, you have the corresponding canonical matrix corresponding to that program. And I have listed in the diagonal of that matrix the variables. You can see the diagonal A, B, C, D, etc. Those are the variables to be initialized. And in the lower triangle of the matrix, I have listed the arguments of each function indicated with an A. For example, the variable L is equal A plus B. So L is a function of A plus B. And you can see that there are two A's under A and B in the row of L. That indicates a dependency, which is precisely a predecessor relationship in the partial order. The red lines are called flux lines. They indicate the flow of information in the equation. If I say L equals a function of A and B, then there is a flow of information from the variables A and B to the variable L. And that flow is indicated by the flux lines that I have indicated in red. Now I started refactoring the program, using my brain for that. So I did it in very small steps, each step consisting of reversing the order of two adjacent statements in the program. In my brain, that's me, I would select which pair of statements to reverse the order. It will tell me, okay, that pair looks nice, let's do that one, I would do that one. Then I would look at it and see, so I refactor manually that program. I thought it was 12 minutes. How long have I been talking? Okay, well, I can manage with that. Here is the refactor program. What I notice is that the flux lines become a lot shorter. And that you see how short they are on the right. The matrix on the right has some structures. And one wonders what the structures are. They are intelligence critical. They may be architectures for the system that is represented here. In complex system science, we work with complex dynamical and dissipative systems. This system is complex. It is dynamical because the emergent inference provides the dynamics, and it is dissipative because it dissipates the length of the flux lines. In this system, intelligence is a side effect of the dissipative dynamics, a side effect. I did not write one single line of code to do that. The brain seems to behave in the same way, where the connections between the neurons correspond to the flux lines. One important question, are the structures observed? Well, yes, they are. In the neurosection just yesterday, the neuroscientists spoke about or presented about observations that they observed hierarchies of structures exactly as predicted by these mathematics. There is a lot more to say. I do not have time, unfortunately, but we can somehow communicate and talk, or I can answer questions sometimes in the panel. I thank you very much to the organizers because of this excellent conference that we have, and I thank you all for being here. Thank you very much.
Okay, so this is a conceptual presentation and a conceptual talk about the relation between rationality on the one hand and general intelligence on the other. Here's an overview of what I'm going to talk about. First, we will start with a very short introduction. After that, I will say something about rationality and two relatively famous challenges that were proposed from psychologists, from the psychological literature, some experiments. The first is the so-called Wason selection tasks. The second one is the famous Linda problem from Tversky and Kahneman, and then we will draw some consequences. After that, I will propose that analogy making and coherence maximization could be good candidates for using them as cognitive mechanisms in order to explain the seemingly irrational behavior of subjects in these experiments, and then I will give some remarks on future research and will finish with some conclusions. Now, first of all, as a matter of fact, theories of rationality are often linked to disciplines like economics, like philosophy, like psychology. In economics, you get Nobel Prizes if you are really good in this field. In psychology, you become potentially a director of a Max Planck Institute. So you can get a lot of honors, I think, if you do this. The situation seems to be a little bit different in classical artificial intelligence, because usually I think only little attention had been paid to rationality issues in classical AI, and not so much different also to artificial general intelligence. I do not claim that this is absolutely was never mentioned or so. So, for example, one could perhaps Markus Hutter's IXI or algorithm or P. Wang's NARS could be perhaps strongly related also to rationality issues, but usually these people talk about other things. They talk about universal intelligence, for example, and not so much about rationality. I think that AGI would do a good thing if they move towards rationality issues in a more direct and more concrete way. Such a theory should not only explain what, in which tasks and in which respect agents act rationally or behave rationally, but it should also be able to explain to a certain extent why such so-called rationality puzzles can occur and why seemingly subjects do something that, according to some normative theories, are not in accordance to some rationality theory. Here's the first example, the so-called Bayesian selection task. The following situation is given. So 4 cards are presented to subjects. On one side there is a number, on the other side there is a letter printed. There's a rule that must be checked by the subjects. The rule is an if-then condition. It can be stated as, if there is a vowel on one side of the card, then there will be an even number on the other side of the card. A clear if-then condition and implication. And then subjects are presented a certain situation. For example, the following that is depicted. You see A, you see D, you see 4, you see 7. The task to the subject is now turn as few as cards as possible in order to prove the rule or to falsify it, right? So, and the minimality, because you can change or turn every card, but that's not the idea. So do it minimally. So what's the right solution? If you apply the laws of classical logic, you should probably turn A in order to check whether if A is a vowel, then on the other side there should be an even number probably. But there is also something in classical logic which is true. So if A implies B, then from not B, not A should be implied. So you should also turn 7. Because if there is not an even number on one side, there should not be a vowel on the other. So the logically correct solution is turn A and 7. And here are some results from arbitrary experiment how subjects behave. So, for example, 46% turned A and 4, which is not the intended solution. 33% turned A, which is not only A, which is not the intended solution. 3% performed good, well, so to speak, made the right thing, and 18% did something else. So they were seemingly not able to perform this modus tollens law rule. Now, the interesting thing is if you put these subjects into a different situation where this is more concrete and is somehow in accordance to what you experience every day, then they behave significantly better. For example, if the new rule is only people over 18 are allowed to drink alcohol, meaning something like, if for someone it is allowed to drink alcohol, he or she must be over 18. It's a completely the same structure, completely different content, but a real world situation in a certain sense. And then you get such a thing that you see a card 15, water, beer, and 22. Then in principle, if you behave as what you would do if you were a police officer checking a bar in the US, for example, but here we need probably to change 18 to 21 or so, but however, then you do the right thing. So what are you doing? If there is some very young person, so a 15-year-old, you check whether this person is drinking beer. And if there is someone drinking beer, you check whether this person is 20 or 18 or older. And if you do this, it's perfectly fine. You solve this problem. Now, in such nice setups, subjects perform significantly better. That's the first puzzle. And the second puzzle I want to mention is the famous Linda problem, proposed by Tversky and Kahneman, 1983. There's a profile given for Linda, which can be stated as follows. Suppose Linda is a 31-year-old, single, outspoken, and very bright woman. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in the anti-nuclear demonstrations. So there's a certain particular profile that was somehow given to the subjects. And then subjects get some propositions or some statements about Linda, right? So, for example, Linda is a teacher in elementary school, Linda works in a bookstore, and so on and so on. The important one of these 8 is number 6 and number 8. Number 6 is Linda is a bank teller. Number 8 is Linda is a bank teller, and she is active in the feminist movement. Subjects should rank according to probability. What is more probable that fits to the profile to Linda? And the interesting thing is that 85% rate 8 as more probable than 6. 8 was a conjunction of two things. Linda is a bank teller and active in the feminist movement. 6 was one conjunct of these two statements. Linda is just a bank teller. This is according to probability theory, and the Kolmogorov axiom is not possible because the possibility of a conjunction of two events cannot be bigger than the probability of a single conjunct of it. So again, they seem to be irrational. So what does these two examples show? Well, it seems to be in the case, at least in a relatively weak formulation, that sometimes subjects have problems to think in classical logic, and sometimes subjects have problems to decide according to the laws of probability theory. Okay. Now, nevertheless, I don't think that these subjects are irrational in a strong sense. I think that subjects and we all together as human beings are extremely smart. It is only that we are no deduction machines, and according to classical logic, we do not think only or exclusively in terms of Kolmogorov axioms. And nevertheless, we have, or let's say we have other strategies as well to address these problems. There are many attempts that exist for resolving these things, in particular very special logic systems that are proposed to model this reasoning in models instead of reasoning with inference calculi, taking into account context effects and so on. I want to propose two relatively general cognitive mechanisms, namely analogy and coherence. That are somehow can be used as different mechanisms that are applicable in particular situations in order to address such problems. Our proposal is to explain these puzzles with these general mechanisms. I think that both are relatively important in the psychological literature and in cognitive science, so analogy making seems to be crucial for human cognition. It may be also a reason why humans are so smart, and coherence maximization, a theory that originated from work by Paul Thaggart, is a theory that models the connection of propositions in subtheories that make something more coherent than some other subtheory. Now, what is the reason why in the abstract case, so where we were talking about numbers and letters in the Bayesian selection task, subjects perform badly? Well, maybe the reason is they were not able to perform an appropriate or to establish an appropriate analogy. This was a completely abstract thing. There was no possibility to relate this somehow meaningful to a situation that fits to the structure, and therefore they need some other strategies, and these were not so successful. The reason why subjects perform significantly better in the beer case, in this concrete case, is because they were able to establish some kind of an analogical only one? Okay. They were able to establish an analogical relation. Namely, they somehow did what they would do in an everyday analogical situation when they are, for example, this police officer that are just needs to check whether people younger than 18 are drinking beer or not. And then they are perfectly fine. Actually, just as a side remark, these experiments were also performed with children in their world, and what is very interesting, even children perform better in some setups than adults, right? Structurally, because it fits to the experiments are designed in a way that it fits to their world. In the Linda case, coherence maximization can be used. So the idea here is that a statement like Linda is a bank teller and she is active in the feminist movements is in a stronger sense coherent to the overall profile of Linda, because that the feminist movement activity is somehow strongly related and coherent with the profile that was somehow given for Linda in the introduction of this experiment. In comparison to Linda is just a bank teller, because Linda is just a bank teller seems to be a plain clash somehow to the profile, right? Because usually people with this profile will not become bankers. And now, to make a long story relatively short, there are computational models for analogy that can be implemented and that were proposed. An example is something we developed in Osnabrück, namely heuristic-driven theory projection. and for the extraction of subtheories for source and target domains in order to establish analogical relations. And a reasonable thing to do is to relate this to coherence measures and to use coherence measures in order to get better subtheories for source and target. Remarks for future research. What would be desirable in general? To integrate cognitively inspired frameworks for modeling rational belief into AGI system, also addressing such particular problems and giving some reasonable explanations. How this should be modeled in such an AGI system. Clearly also a variety of mechanisms should be used dependent on the information state the agent or the program or the system is in, background knowledge, available resources, contextual embedding, time restriction, and so on and so on. So the usual thing that are, by the way, usually by psychologists quite often not sufficiently taken into account. What would be desirable in particular for our approaches? That good coherence measures for the extraction of source and target theories would be a good thing. Good coherence measures for mapping and re-representation in the analogy process is a necessary thing. And there are some tension, they are a little bit specified in the paper, between classical theories of coherence and HTTP. They need to be resolved, but I don't think that they are not solvable. Here's the final slide, conclusions. The take-home messages, rationality did not get sufficient attention in AI and AGI. I would like to change that. Rationality puzzles seem to show that humans use a variety of reasoning mechanisms and not just one. Computational models for analogy and coherence exist and are good candidates for that. And in particular, heuristic-driven theory projection is an example of a computational theory that can be used for implementing this. Thank you very much.